best also. In that fuels better and best some of the problems in this solar energy and including fuel cells, no drawback characteristic features. So far we can concentrate it on more fuel cells as well as including of the what we can call it as solar energy. So in this solar energy and fuel cells, we can select it also, we will use it also. Nowadays also we are using of these type of fuels also. In that solar energy, solar cells, photovoltaic cells, solar cookers, everything is solar made out also is there. So in that what the advantages are more, it is no need of recharging, operate these in all the days also. It is eco-friendly, no corrosion at all. Fuel source is plenty, low operating maintaining cost, low that is wear and tear, and reliability is more than 20 to 30 years. Excellently safety also, it is modulars, everything also. The problem is only this, it is completely dependent upon the intensity of sun, and it is the next is the efficiency of solar cell not so much exact, because it is below 20%, maximum is 30 in the days of summer days, and including these near these too much of hotness, more than 30 35 40 degrees centigrades of temperature is there. At the time we can get it as that. So as the same way, it is the another problem is it is only working in the days. Of course, in the after the 10 o'clock, near the 4 o'clock. So and all those things along with this, because of its reduce of efficiency, theoretically what we have calculated is one cell, it can generate the half voltage, that is 0.5 voltage by one cell. It means you want 10 volts 20 cells is enough, but you can making it a frame and you can modulars and you arrange it. So this is only the generation of DC currents. It requires the storing a grid also, that is conventional batteries or any storage devices we require also, that is cost. The initial cost is too high. As the same way afterwards, the out of this 20 cells 10 volts, it is only 20%. It means 1 or 2 volts as a stored, not more than 30% of energy as stored in that grid so far. So the problem is the increasing of conversion portion is increasing from 20 to 30 to 60%. Then it is more useful to us. At least out of the 10 cell for 5 volts, we can insist for 15 cells also. So in this manner, so we can get it as at the time very easily, we can install it also, we can use it also, we will become very stable also, having the strong and best economy of the state and country also. For this, what we have done is, we are using the silicon. Why do you using the silicon? Because it is plenty of availability, 23% of the maximum element is present after the oxygen is only the silicon. So it is a metalloid also, so it is semiconductor also. So we have used to manufacturing of solar cells. So when we are this using of this manufacturing the solar cells, at the time what we can do, we the making the mining to that, the extraction of that from the earth crust, then it directly use not like it is not even a primary source of fuel also, secondary fuel also, or even tertiary fuel also. You will call it as a more than quaternary. It is just of this joke what it is. So it is the whatever we can extract from that earth crust, that is a silicate, is the silicon is in the form of silicate. Silicon is in the form of SiO2. So that silicon is in the form of O2. it is not useful for any purposes. It is only the use for kept in this house also. So afterwards, what is, we will remove it whatever the impurities are there, whatever the impurities are there. So we should remove it. Then we will try to use it as a semiconductors. So for that process is making into these semiconductors and conductors, all those things are there. So for the topic is the production of solar grade silicon. So the topic of this production of solar grade silicon, they have given one more on the additional name as a union carbide method. So this is the new method. From this new method, we have used to synthesize of solar grade silicon. So what is this solar grade silicon? It is 100% purity of silicon. We can call it as a solar grade silicon. So even 100.0001 or 2% of impurities are there. That is solar grade. Again, it is done by this zone refining method. 100.000, any number you can put ppb. Also, no impurities at all. That type of the silicon, we can call it as a ultra pure silicon or pure silane. We can call it as ultra pure silicon. So these, and we are naming to this silicon to that. What we have again these extract and the mining from the earth crust, that is we can call it as a metallurgical grade silicon. So metallurgical grade silicon converting into a semiconductor grade silicon, then semiconductor grade is converting into a solar grade silicon, then solar grade silicon is converting into as ultra pure silicon. Either ultra pure silicon or solar grade silicons are used to manufacturing of solar cells, whether it is metallurgical grade silicon or just of the silicates. We should not use for this preparation or manufacturing of solar cells. So further, some process is required. What you can extract the silicon or silicate from the earth crust, then it is you can taking into these crucibles, and that is what we can call it as silica. Then that is keep it into the crucible and using the electric arc method or any other methods also you can use it, that connected with this crucible to electrodes and placed in the crucible, making into this quartz and code the electric arc. When we are using the electric method, at the time silicon dioxide plus carbon, that is electric arc method, so we can get it as silicon plus 2CO. Silicon plus 2CO. SiO2 plus 2C gives rise in the electric arc method. So we are using the graphite as a crucible at the time. So this silicate become silicon and two molecules of carbon monoxide as formed. So these two molecules of carbon monoxide as formed. So at the time in the metallurgical grade silicate is 190 to 95% of silicons are there. Remaining 10 to 8 or 10% of impurities are there. Not only the calculated amount, beyond that any of these, not only silicates, some other metals is also there, any of these dusts are there, everything after cleaning of all those things, then pure silicate means what is inside the impurities are there. In that pure silicate also 90 to 95 to 96%, remaining 4-5% of impurities are there. That a silicate is subjected to the electric arc method to separation of silicon from silicates. Then that at the time we can get it by arc method is 98% of pure silicon we will get it. So then for this 98% is not useful also. It is mixed with, again it is mixed with some flux. So what are these flux are we are using as aluminum, calcium, magnesium, all these things. We can separate it of that 98% of silicon. Then it is we are adding of calcium. At the time we are also going to eat it. In that eat it, so at the time this you can add one more aluminum, calcium, including of magnesium also. Automatically this silicon plus aluminum, any minute oxides are there at the time, the silicon plus aluminate. See, calcium plus silicates, because why do you write it as again silicates? This is 98% of silicon is there. What about remaining 2%? Oxygen is there, oxide is there, silicate is there. So that so we can write it again that these 4 molecules of aluminum and 3 molecules of SiO2, we can get it as 3 Si plus 2 aluminate. As the same way, calcium plus silicate, so calcium oxide and silicon. And magnesium is also you can eat it. So at the time magnesium oxide and silicon. So now also this using a flux plus gang we can produce as flux is infusible impurities are there in the elements in the ore, we can remove making it as a fusible ones. The reaction of this flux is with any infusible impurities forming into that respective compounds and separation of another compound. That is another metal or another compound. That we can get it. So this, after this electric arc method is, we can get it as a 98%. From this 99% of 99.12% of silicon we can get it. So still it is we want only the 100% of silicon for manufacturing of the solar cell. That is we can call it as solar grade silicon. For to manufacturing of this solar grade silicon, this Si is silicon is heat with 3 molecules of HCl. Now we can taking 4 molecules of HCl also, heat with more than 300 degrees centigrade. So at the time this we can taking it as 4 molecules. The 1 molecule of silicon, it is completely so tetrachlorosilane as formed. Heat it with up to the 300 degrees centigrade. It is the mixture of trichlorosilane or tetrachlorosilane as formed. So the mixture is also separated. So whatever it is there, trichlorosilane as formed, you can separate it. Again you will eat it with 1 molecule of HCl. Completely the silicon, the metallurgical grade silicon. Now it is we can call it as metallurgical grade because it is impurities very less also. Even it contains impurities also. So that it is it is heated with 99% of silicon is heated with 4 molecules of HCl. Completely we will get it as a tetrachlorosilane, SiCl4 we can call it as chlorine 4. So we call it as tetrachlorosilane. So this tetrachlorosilane is then subjected to this hydrogenation. So it is adding with this hydrogenation. In the old method we can call it a Siemens method. At the time again it is heated with HCl, but we can after we prepare the tetrachlorosilane in the union carbide method, we should not use the HCl again. So for that type of the method we can call it as a union carbide method. So in this union carbide method we can separate the trichlorosilane and tetrachlorosilane. So whichever the part is the tetrachlorosilane on the base of silicon crucible, or we can call it as tank or whatever is on the base of crucible, we can subject it to this hydrogenation. So that is 3SiCl4 plus 2H2 plus Si. What is this Si means? The base of this, the container base is made out of the silicon. That's all. In the olden is again it is the old method, react with the HCl, then hydrogenation, then again it is HCl, then ammonium tetrachloride, then it is forming. By Now it is avoid to that we are using of this pure silicon crucible. In that we can taking into this tetrachlorosilane and two molecules of H2 hydrogenation subjected to this hydrogenation. Then we can get it as a four molecules of HSiCl3. That is, we can call it as a trichlorosilane. So this trichlorosilane along with this hydrogen is also there. So this trichlorosilane is again subjected to this passing into this quaternary ammonium ion. So quaternary ammonium ion, you can pass it, heat it to this more than 600-700 degrees centigrade. At the time you can get it as a dichlorosilane. So tetrachlorosilane become trichlorosilane. So then it is again subjected to this trichlorosilane into this passing into this quaternary ammonium ion. At the time you can get it as H2SiCl2 plus SiCl4. This tetrachlorosilane is separated. Again it is conducted towards of this, the first method of it is in the crucible of silicon, and again it is converting into as a trichlorosilane. So already we can tetrachlorosilane we can separate it. Then it is subjected to this hydrogenation again, that dichlorosilane is subjected to the hydrogenation. We can get it as a silane. That silane is SiH4. We can call it as a silane. So this silane no containing of chlorine. So SiH4 we can get it. The mixture of trichlorosilane also we can separate it. So that separated of silane, and that is silane, it means SiH4 is again subjected to the pyrolysis. It is too much of heating, more than 1000 degrees centigrade. At the time what we can get it, the 100%, 99.9999% of silicon you will get, hydrogen is also separated. So this is, we can call it as a solar grade silicon. Solar grade silicon. So this solar grade silicon, if you want ppb, ppm means parts per million, ppb in 1 milligram is also not there out of this chlor together percentage also not there. At the time these pure silicon, solar grade silicon subjected to this zone refining, at the time we will get it as a very exactly 100% of silicon, that we can call it as a ultra pure silicon. Before you can get the ultra pure silicon also, 99.9999 very negligible. This ppm methods of impurities are there, no problem. So this silicon we can call it as a solar grade silicon. So three types of silicons are there. Metallurgical grade silicon, what we can extract from that, the crudely we can removing of any impurities are there, that is subjected to the arc method. 98% of silicon is there, we can call it as metallurgical grade silicon. Then making into this 99-100% of silicon, that is semiconductor grade silicons in 1 or 2%. After you can using of this flux, you can separate it, that we can call it as semiconductor grade silicon. We are using for any of these other electronics uses. At the time no problem, but for making into the solar grade, the solar cell, again it is subjected to heat with the HCl. Then you can forming into as tetrachlorosilane. So that tetrachlorosilane is subjected to this union carbide method for hydrogenation. You can get it as trichlorosilane. Again subjected to this quaternary ammonium resin. At the time you can get it as a dichlorosilane. So then it is again subjected to the 2 times of hydrogenation. Finally you will get it as silane, SiH4. This SiH4 is a pyrolysis subjected to the pyrolysis. At the time you can get it as hydrogen is separated and silicon is separated. This silicon we can call it as a solar grade silicon. That is 99.999%. So it is used for the preparation of solar cells. This process is, we can call it as a union carbide method. So the old method, again we have HCl is used to converting into a trichloro dichlorosilane, but in union carbide method, after it has forming into the tetrachlorosilane, we need not to use, we never use it to again the HCl to converting into as a silane, or finally 99%. So generally, so what is this? This metallurgical grade silicon, it is a crude silicon. It contains the impurities also. Afterwards, we can remove the impurities crudely. Then we subject it to the this after the arc method. So we can get it as using of the flux. The arc method is used, that is we can call it as metallurgical. Then it is subjected to this heating with the flux. We can get it as a semiconductor grade silicon. So after this semiconductor, so it is in 1% or 0.5% of impurities are there. But we want that, so then it is, we can remove again this any impurities by this union carbide method. At the time we can get it as a solar grade silicon. But this is not possible to make it usable, very excellently usable. But again we will doping it. It is intrinsic silicon. It is intrinsic silicon. Doping of these phosphorus families, that is nitrogen families, we have pentavalences and trivalences mixing. That is dopants, you can add it. You add it of dopants, what is that? That is also impurities. This adding of dopants is desirable impurities. The whatever the undesirable impurities are, we can call it as a killer impurities. So far, after you can get the solar grade silicon, after then you can adding of these impurities, this position is again getting of second position. First is metallurgical grade silicon, second is a solar grade silicon, then is semiconductor grade silicon, because 2 to 3% of impurities are doping of boron families and including of phosphorus families, we can adding to that, then it is using as a PN junction. That PN junction, making the thin wafer, thin slice, you can make it, then it is using for to manufacturing the solar cell. You pasting on this any glass frame, so at the time it is absorbed and converting it as a electrical energy. So this is the third module, repeated after the madam is completed, also myself is also repeated. In this module, one numerical problems will come. So first module, one numerical problem. Second module, no numerical problem. In this third module, one numerical problem is there. Afterwards, fourth module also one numerical problem is there. So these numerical problems, it is easy to also, it is look like a fifth standard types of numerical problems. Just the values are there. You can substitute the values and you can get the answer. But in this, substitute the answer and you will get it very exactly. You find out the gross calorific value, net calorific value, and you find out the in the first module is what is this potential or concentration cell, whatever it is, they will ask. After the point we can calculate the 4 digits. Don't make small mistake also. 99.99 we want, we will first you will write 99.999, then you make it as converting into 100. Directly you will write 100 also, they will cut the marks. So far, what you will get the exact values, you will write it. After the digits, 4 digits also we can consider. So this is the second numerical problem. The third is in this to find out the COD and BOD. In that COD, only direct question is there. So these three problems, first is already we have done in the class itself. For second, so before starting of the classes, I have sent what is that to find out these. You can keep it here nearby. Already take photos. If it is not taken, also just I will explain what is this one numerical problem. This on burning of 0.76 into 10⁻³ kg of solid fuel in a bomb calorimeter. So this whatever I sent this in the photo copies of this to the group, you can all the numerical problem individually you can solve it. You apply it, you read this and write the values, substitute the values. First you can very neatly you can write the data, so then you will solving it so very exactly, so that exactness is at the time we can read it. So I will read it with the help of these notes. On burning of 0.76 into 10 to the power of minus kg of solid fuel in a bomb calorimeter, the temperature of 2.5 kg of water is increased from 25 degree to 28 degree centigrade. The water equivalent of calorimeter and latent heat of steam is 0.486 kg and 2457 kg kilojoules per kg. So respectively, they calculate the gross calorific value and net calorific value. The specific heat is 4.187 kilojoules per kg per degree centigrade, and percentage of hydrogen is 2.5. So for any of these numerical problem in the find out the calorific values, these minimum values we require. Finally, to substitute all those things, we will get it as a we will get it that final answer. So what is that? The weight of the solid fuel is 0.76 into 10 to the power minus 3. So everything you will going to changing into the kg. Suppose they have given in the gram also, you can taking into as kg into multiplied by 10 to the power minus 3, you will write it. So it is because what is the unit is calorific value is joule per kg. If you want to, you can convert it into joule per gram also. So this more bigger value is calorie. So calorie joule per kg, calorie per kg. So now it is changing it as joule per kg. So this 0.76 into 10 to the power minus 3 kg. The weight of water is 2.5 kg. So and that is what we can call it as temperature is directly they have given increasing temperature also one values by 3 degree, or they were given two values T2 minus T1, you will get it as a 28 minus 25 3 degree centigrade. So water equivalent weight is also they have given, that is 0.486 kg. They have given completely everything is in the kg, there is no confusion at all. If they have given only the gram for this mass of that fuel at the time, you multiply it by 10 to the power minus 3 kg. So both the values are same. So specific heat is 4.187 kilojoules per kg per degree centigrade. So now we can the substitute of all these values, the percentage of hydrogen is helpful to calculate the what we can call it as a net calorific value. So for at this gross calorific value formula is you will write W plus W1 or M plus M1. Better is weight is that W plus W1 into T2 minus T1 into specific heat, that is divided specific heat per kg per joule per degree centigrade. You can applying of this what we can call it as 2.5 kg plus 0.486 into 3, temperature is 3, specific heat is 4 into 1.87. They have not written the units because kilojoules per kg, so per degree centigrade. The temperature is also degree centigrade. This per and that everything is going to cancel. Finally, we will having only the numbers. But this number is only this kilojoules per kg. Everything is you can calculate, that is 49,351.5 kilojoules per kg, you will get it, because you can cancel all those things. Remaining unit is there, retaining is kilojoules per kg, you can get it. For net calorific value is equal to gross calorific value into 0.09, that is formula. Percentage of hydrogen is 2.5 they have given, and latent heat of that is also the specific heat is 4. The latent heat is 2457. Yes, we can search it. Here is there. And 2457 kilojoule respectively. The calorimeter latent heat of steam, that is 2457. So we can substitute latent heat of steam is required for, and percentage of hydrogen is required for, only to calculate the net calorific value. That is, the gross calorific value is 49,351.50 kilojoules per kg. Net calorific value is 48,798.67 kilojoules per kg. This is very minute, around below 1000. It means 95% of energy will going to change one form to another form. Then it is will going to changing into this very minute to that, not too much. So almost all we are given 0.5 gram, 0.5 gram or 0.5 gram into 10 minus 3 kg you will converting into also. It means above the 45 something you will get it. So below of this, below of the 0.5 gram, now it is we will get it as around 25,000 something answer we will get. So far in this, only this type of numerical problems you will going to answering for all those things. So this is the second numerical problem. You will see I have given in that you will show your separately you done it and take the photo and send me everyone to me. So this whatever the numerical problems we have typed in the question bank, you should separately answer and send to WhatsApp individually. You put your name, you take the photo and send to me. I will value everything. Afterwards, I will respond to that. So in the fourth module, environmental pollution and water chemistry. So in that is we will simplest forms of numerical problems are there. That is I can send it also. I sent to you, already I sent you. That is, calculate the COD of the effluent sample when the 25 centimeter cube of effluent sample requires 8.5 cm cube of 0.001 normality of potassium dichromate solution for complete oxidation. We will calculate the COD. So, but that COD, before that we will going to COD call it as N1 V1 is equal to N2 V2. So, N1 is normality of our given water sample. So, is equal to N2 V2 divided by V1. So, how much of we will pipette out? That is in the denominator. 25 ml they have given, we pipette out 25 ml. So, N2 V2, normality of potassium dichromate is.
Sir, voice is cracking, sir.
What, man? You go to the fourth module. I have sent that photocopy to you.
Sir, voice is cracking.
Voice is not clear. Hello? Durga Prasad?
No, sir.
Voice is not clear.
Yes, sir.
In the third
No, sir.
Now? Now is also not clear? Hello?
No, sir, no.
So regarding I am going to explaining for numerical problems. Follow. In that numerical problems, in the chemistry, 3 numerical problems are there. In that 3 numerical problems, one from first module, second one from third module, third one from fourth module. So I think you will attend first question and third question. Third and fourth question it is coming under the third module. First and second question from first module. Second and third question from the third and fourth question from second module. Fifth and sixth question from third module. Fifth and sixth question from third module. Seventh and eighth question from fourth module. Ninth and 10th question from fifth module. I think this is clear. 2 questions from one module. So we want to give it is more chance to you attending of 3 numerical problems. I think I am clear to you. In that, whether it is first question or second question, one numerical problems we have solved in the classroom. In second numerical problems is coming under the question number 5 and 6. In the question number 5 and 6, it is coming under the third module. We will going to find out the calorific value, that is gross calorific value and net calorific value. So there is one numerical problem. In next, in the fourth module is question number 7 and 8. Question number 7 and 8. So out of these 10 question, you can completely attending the 5 question. So question number 1 or 2 you will attend, one numerical problems is there. Question number 5 or 6 you try to attend, one numerical problem is also, another numerical, second numerical problem is there. As the same way, in the third numerical problem, in the question number 7 and 8, 9 and 10th is the under the fifth module. So for you will see the question paper first, try to answer into those, whatever already I sent to you the numerical problem solving from the some other books. So you will see that just you can write the values to that. So for gross and gross calorific value and net calorific value is equal to gross calorific value for W1 and W2, weight of water, weight of calorific water. So both weights are they given, you will add it and write. Then degree of temperature is rising. It is actually 2 degree or 3 degree is rising at the time of heating the fuel. Then is specific heat of the given sample. Whether it is you taking the coal, you taking the wood, you taking any other things, specific heat also they have given. You can apply, you write it, divided by what is the amount of fuel you have taken. So completely you will get the answer is the kilojoules, more than 40,000 it will come. So because we have taken the minimum at least more than 0.5 gram. So as the same way we can going to find out net calorific value is equal to gross calorific value minus of 0.09. It is the equivalent weight of water percentage into percentage of hydrogen is there, how much in the fuel they have given, into latent heat of water stream 2457 kilojoules per kg. So that is they have completely they have given. You will substitute, you will get the answer also. If you got any confusion, separately you will solve it and we will write it and send in the WhatsApp. I will check it. Okay. So this is the question. As the same way coming to the 7th and 8th question, so you find out the COD and BOD for easily asking to you. At the time you can write it as N1 V1 is equal to N2 V2. In this example of I have sent this define COD under that one small numerical problem is there. So afterwards 3-4 numerical problems also I have given to you. Just you will solve it. At the time of solving you can call me through WhatsApp call or this video call also. Then you will helpful to you to solving to those. You write it and then that is N1 V1 is equal to N2 V2 for this COD. N1 of this is we will going to find out is equal to N2 is 0.001 into 85, that is 85 ml of potassium dichromate. So you can write it and divided by 25. So what you can get, that is normality of given wastewater sample. Multiplied by oxygen molecular weight is 8000, you will get it as that. So because you have taken 25 ml divided by 1 ml, so divided by 25, so that you can get it as, that is we can call it as the, what the answer is the COD. That COD answer you will get it. So for every day you concentrated on numerical problems of these 3. So you will expect 21 marks is easily you can get it. So within half an hour. So half an hour is enough to solving the 3 numerical problems. So then it is we can get it as easy. And one the next question is what is that first module, Nernst equation derivation. Nernst equation derivation, for whatever the too much of important questions I will send to you. So one list. So according to that list, you will write it and tick it also. Send again to me also. So we will clarify to those things. Whatever the topic is not understanding, so immediately you can get it. So we will solve your doubts. So I think so. This let me start the fourth module. We will ready to start. If not, we will go to this. This is what we can call it as today's is 45 minutes. So in the fourth module, it's environmental pollution. So in that environmental pollution is already we have discussed also. In that environment, it is a very familiar term also. You will is day by day it's degrading of its what is its naturality, degrading of its quality. So that degrading of quality by physically, chemically, and biologically. So all those things at the time, so we can get it as finally we find out how much of it is impurities are there. All those things we will get it. So at the time, what are the substances? What are the substances are expelled into the atmosphere? What are the compounds are expelled? What are the things you can be adding to the atmosphere at the time? Which are those reducing its qualities? So those substances are, we can call it as a pollutant. Environmental pollution. What is environment? Which is the surrounding of us. It includes both biotic and abiotic factors. Biotic factors are living things. Abiotic factors are non-living things. Both of it surrounding us to the end where it is infinities. The radius is not so small. So whatever in that biotic and abiotics interactions are there, afterwards interactions are over, degrading its quality of the environmental, we can call it as a environmental pollution. This word environment is environmental pollution is derived from French language. That is analysis of that so interactions and reduction of its qualities. But why it is day by day it is increasing this type of the problem is because day by day we are industrial numbers are increases, urbanizations also increases, number of vehicles is also increases, that is population is also increases. Because of all these things, so this the environmental pollution is going day by day it is increases. So that is one of the example of in the last year, what is the Delhi, that is too much of particulates matter, that too much of mist is there even in the mornings also, evenings also, except the middays. So because of too much of impurities, too much of end products discharged into the atmosphere, that is we can show it in the morning times and evening times. So undesirable change of environment physically, chemically as well as biological, that characteristics of environment, whether it is directly from human beings or indirectly from human beings, or it is from natural environment also, the changing the characteristic feature, that is undesirable changes, not acceptable, not desirable. So it is undesirable changes of physical, chemical, biological characteristic feature of environment, we can call it as environmental pollution. So whichever these substances keep on add to the environment, those are react with already existing of components of the environment, the forming into its products. So that is we can call it as a pollutant. These pollutants we call it as primary pollutants. For example, we are expelling of after using of the vehicles, burning of fuels, carbon dioxide and water. The water is no problem. This carbon dioxide is pollutant. This is we can call it as primary pollutant. Why? Because it react with the components of the atmosphere, and it forming into as it is their carbonic acid is formed. So this forming into as its compounds that is from whatever the components are there in the environment, then that is we can call it as primary pollutants. So carbon is, if carbon soot is entered, oxygen is there, react with the oxygen, carbon dioxide is also formed. So carbon dioxide will directly enter into the atmosphere, nitrogen directly enter into the atmosphere, sulfur dioxide enter into the atmosphere, hydrocarbons are enter into the atmosphere, or even including of what we can call it as a any lead particles is enter into the atmosphere, any mercury particles are enter into the atmosphere. These are we can call it as primary pollutant. Primary pollutant, this is a compound produced from human beings or nature directly into the atmosphere that will ready to changing undesirable changes of the environment. So after it is undesirable changes, when compound has formed, so that compound is again react with the components of a environment. So those type of the products we can call it as secondary pollutants. The primary pollutant examples are carbon dioxide, nitrogen dioxide, sulfur dioxide, hydrocarbon, particulate matters. The secondary pollutants are called carbon monoxide, carbon dioxide changing into the carbonic acid. That is secondary pollutant. Nitrogen oxide forming into the nitric acid. That is secondary air pollutant. Sulfur dioxide forming into sulfuric acid. Sulfuric acid is a secondary air pollutant. So hydrocarbons is forming into as again it is carbonic acid and H2SO4 or HCl is formed. That is secondary air pollutant. Particulate matter also forming into it is we can remove it. This is only the primary air pollutant. No other again the compounds are formed into the atmosphere. So these are primary air pollutant. These again react with the compounds of components of the atmosphere forming into a secondary. Secondary air pollutant is ozone. Ozone depletion is also there. So it is the one of the thick layer more than 1 meter to this 5 meters of thick near the above the 50 kilometers 35 to this atmosphere is again divided into this up to 30-25 kilometers. We can call it as a troposphere, stratosphere, so mesosphere, ionosphere, exosphere, thermosphere, like this. So up to this 25, 30 and 25 kilometers, we can call it as a thermosphere, what is troposphere. More than that, up to 50 kilometers, we can call it as a stratosphere. Above the stratosphere from 50 to 80, 30 kilometer distance, we can call it as a mesosphere. Above the mesosphere, 120 or 120 kilometers, 80 to 120, we can call it as a what is that ionosphere. So above the 120 to 300 kilometers, we can call it as a exosphere. So more than 300 kilometers, we can call it as thermosphere. In the thermosphere, above the ions, nothing is there, only simply empty space. So before that, in one